Hi, Charles. Happy to have you here.
Great, thank you for having me.
Go ahead.
Okay, my name is Charles Martin. I run a boutique consulting firm in San Francisco called Calculation Consulting, where we do projects for companies to try to help them develop AI solutions, mostly in the tech space, natural language processing, text generation, search relevance, something we're very good at. Today, I want to talk about a tool I've developed. It actually came out of some of the work we were doing to try to understand how to train transformer models and figure out whether they're working or not for problems like text classification, text generation. It's called WeightWatcher, and it's a diagnostic tool for deep neural networks. And this is work. I've been working for a long time in the industry. I've worked with a lot of companies. Been doing this for over 15 years. I was at Aardvark, which was acquired by Google over a decade ago. eHow, which we use machine learning to basically say reverse engineer Google's PageRank algorithm, things like this. I've worked at a lot of different companies over the years, from Wall Street to Fortune 500, Walmart, Roche, France Telecom. So I've seen a lot of things. I also do some work in the alternative energy space with the Anthropocene Institute. And it's actually kind of nice. Our WeightWatcher project's been used for a project to help people figure out where to plant trees, try to help out with the environment. But today I'm going to talk something very technical. This is a project which has been based on research I've been doing with an old friend of mine, Michael Mahoney at UC Berkeley, who's a specialist in randomized linear algebra and machine learning theory. So Michael sort of came to me maybe a decade ago. We were at a conference talking about this new emerging field of deep learning. And we were talking about, look, there's a lot of connection to things we were doing in theoretical chemistry back in the 90s. And we just started talking and talking and talking, and we realized we could make some deep theoretical advances. And this has led to a number of papers, but has also led to a tool. So the motivation has been, we've been trying to understand why deep learning works. Why does it work at all? We have this tremendous advance that's going on in AI. But if you look at it from an academic perspective or a scientist perspective, we don't have a really good understanding of why this stuff even works. And so if you don't understand why it works, it's difficult to build a system that is systematic, where you can test it, where you can monitor it, where you can improve it. It's just very hard to turn it into a rigorous engineering discipline. So our motivations for this came from looking at it from a variety of academic problems and things like the statistical mechanics of generalization, random matrix theory, strongly correlated systems, all really, really nerdy stuff that I studied back in the 90s when I was a student and a postdoc in theoretical chemistry and theoretical physics. But today what I'm going to do is I'm going to talk about this tool. So we've used the theory to develop a tool. I'm going to show you how the tool works for people who are developing their own large transformer models for text generation, say, and what you can do with the tool to help you diagnose problems. So the idea is that you have some model that you've created. It's one of these models, and maybe it's a model you're trying to fine tune, or maybe it's one you're trying to train from scratch. And you take the model and you put it into the tool. And the tool will then take a weight. It will look at the weight matrices at each layer of the model. It goes through the model, looks at the weight matrices, extracts them out. Then it forms some spectral analysis and computes a histogram of the eigenvalues. So it's like having an oscilloscope for a model. You have some model that you're training, you're trying to train, you're trying to understand. You want to peek inside the model and try to understand how well is it performing. And so the WeightWatcher tool will allow you to do this. In fact, this comes from a paper we published in Nature, where we described a lot of these things. So a lot of these things have been published in the literature. We'll describe it now, try to make it clear what are the things that we know really, really well that have been published and fleshed out, and what are the things that are very experimental that we're trying to understand. But it's a very simple tool. If you're a Python programmer, all you have to do is say pip install WeightWatcher, and that installs the tool. Then you import it into your code base. You say watcher equals WeightWatcher, model equals model, and you say watcher describe, and that will give you a data frame which describes the model. It basically shows you how we label it, how we label the layers, and what you what to expect later. And when you say watcher.analyze, it gives you a results, which is a table, a data frame, like a spreadsheet of quality metrics about your model. So you run this tool and you're going to get a quality metric for every layer in the model. And you can look layer by layer to understand how the model is performing. That's the basic idea. So again, it's a diagnostic tool. It runs on systems like PyTorch, on Keras. We have some basic support for ONNX. It allows you to inspect models that are difficult to train. It lets you gauge improvements in model performance. And it lets you do things like predict test accuracies across models without needing access to the test data. You just give me your model and I can give you a quality metric. And therefore, it allows you to detect problems when you're compressing a model or when you're fine tuning it. You can detect problems that arise. So if you're in a company and you build a model and you're building models every day or you're fine tuning them, downstream in the process, we can detect if a problem occurred and you can go back and figure out what happened. So it's almost like a model alert system. So again, it's based on a number of theoretical papers we published, JMLR, Journal of Machine Learning Research, ICML, and KDD, which are these big AI conferences that we have, Nature Communications, which is a fairly prestigious journal. Nature is probably one of the top 3 scientific journals in the world. And we have other papers. There's a paper called Contest Postmortem. There's one where we're training transformers, so things that are in press today under review, and a number of unpublished experimental things. So again, during the talk, I'll try to make it clear, what are the things that have been published in very high quality journals? What are things that are under press today that are still under peer review? And what are things that we just want to try to do with the tool that may be useful to you, but we haven't really published and may or may not be accurate to, it may or may not work. So what is the basic idea? When you have a neural network, you can peek inside it. And when you peek inside each layer, many of these models could have 1,000 layers, maybe a couple hundred layers, maybe 1,000 layers. Each layer represents some amount of information that the model has learned. And from an engineering perspective, the problem is that you don't really understand how the learning occurs layer by layer. So when you build a model or you're trying to fine tune it, all you can really do is look at the test accuracy and ask, is it performing well? And that sometimes can be very hard. And so what we'd like to do is peek inside these models and ask how well do they work. So when you peek inside, you get a graph that sort of looks like this. It's on a log-log scale. And this is what we call the ESD, or the empirical spectral density. For those of you who did any math, it's just the eigenvalues of the layer weight matrix. And you plot it. And the tool will plot this for you. And what you find is that the shape of this plot tells you a huge amount of information about whether the tool is working correctly or not. Whether the model is working correctly or not. There are cases where you see this is called X-min here, where we find the tail of the ESD, which is sort of the tail is where the information is contained. If this shape has a nice triangular shape like this and it's nice and smooth, then we think the model is performing very well. If the tail starts much later over here and the shape is sort of distorted, then we think that something's wrong. And what's different about what we're doing, which is what a lot of statisticians do in theory, is that they'll simply look at the scale. They look at this orange line and say, well, if this line is too large or this line is too small, the model can't perform. But that only gives you like a worst case scenario, which worst case is used if you're trying to do like risk models. Worst case is important. But if you're trying to understand just on average how well your model is doing, did you break the model when you were training it? Then you need to look at the shape of this plot. And that's what the tool does. The tool will take your model, it will analyze the shape of this plot, and it will tell you, is your model working correctly or not? So again, it's very simple for those of you who are software engineers. We're just computing the empirical spectral density, just the eigenvalues of the correlation matrix. It's literally code that sort of looks like this. Obviously not this simple, but this is the basic idea. We import the model, we import some Python mathematical library, we have a plot package. From the model, each layer, we get the weights, we get the shape, we form the correlations in the model. In other words, what kind of correlations did this layer learn from the data? Then we compute the spectral density and make a plot. This is basically what we're doing. When you run the tool, again, you'll get a spreadsheet, or a pandas data frame, a table. And this table contains metrics. And these metrics are things you can plot or things you can look at, and they will tell you how well the model is doing layer by layer. In other words, they're quality metrics. So again, we label the layers. So there's some labeling convention we'll have. Sometimes the layers are named, sometimes they're not, depending on your model. And then you have all these different columns which represent different quality metrics. And what I'm going to do is explain to you how these quality metrics relate to the performance of your model. So one of the interesting things that we discovered is we looked at hundreds of models and thousands of layers. And what we found is that all of the layers fit a power law distribution, a Zipf's law. So if I were to plot this, if I plot on a log-log scale, I get some power law where there's an exponent alpha, and the alpha usually lies between some value like 2 or 6. And it turns out that that alpha is just basically the slope of this line. You know, how steep is it? How steep is this line? And when alpha is smaller, layers seem to do, the models on average seem to do better. This is quite surprising, but we'll show this. And we have a theory, even a theoretical, from some ideas from theoretical physics, which explains why. But here's an example of, you know, and moreover, when you look at the tool in detail, before I go into this, the tool is actually a specialist tool. So it gives you all sorts of plots on there are different ways to look at the layers and analyze them. And I won't go into those details, but basically the idea is, go ahead.
Charles, there's a question in the chat. I'm not
Oh,
sure.
I don't, can you read it to me? Because I'll load it up. Hold on. I have a completely geeky question. Is the weight associated with a probability or amplitude in a quantum sense? Kind of. The theory, if you want to dig into the theory uses some techniques from quantum field theory to represent the error at each layer. And when you write down a theoretical expression for the error, it turns out to be something called an HCIZ integral, which is the type of integral that occurs in quantum gravity and some other and quantum statistical mechanics. So yes, in some sense, it's like that. And if you want, we can go into the deep theory and I can explain that here. But yeah, actually there is some quantum mechanics in here to try to explain what's going on. I was trying to avoid that level of detail, but yeah, that's exactly how we formulated the theory, in fact. But here's an example. So, and in fact, I'll point out, this is really a physics theory. And by a physics theory, I mean, it's a phenomenological theory. So it's sort of going back to nuclear physics, you know, prior to World War II. And nuclear physics prior to World War II is a phenomenological theory, meaning people looked at experimental data and they made models. And so what I'm doing is I'm looking at experimental data and I'm making models. So we're trying to ask, let's look at all these hundreds and hundreds of pre-trained models that people have made and they're using to complete sentences and to correct your grammar and to generate fake text. Let's look at these models and ask how they perform. And let's see if we can build some sort of physics theory based on our experimental observations. And that's why what we're doing is very, very different than what people in statistics do or machine learning research, where they're really looking for a formal theory, you know, an exact rigorous theory. We're looking at more of a pre-World War II type phenomenological theory. And then later we'll explain sort of how you can cast it in the language of quantum mechanics. So this is a good example of one of the experiments we did. Let's take a look at one of these models, GPT versus GPT-2. Now, these models, a few years ago, these were pretty popular. Now they're, you know, sort of baby models. But a few years ago, OpenAI released a model called GPT. And they had this claim, GPT can generate fake text. But oh my goodness, generating fake text will generate all sorts of fake news. We don't want people to do this. So we're not going to train the model on enough data that you can do any damage with it. So they created this sort of junky, low-grade GPT model. Then later they said, well, no, you know, it turns out that generating fake text might be useful. So we're going to retrain the model on more data. And you have to realize these models can take several $1 million to train. So it's not a small thing to build these models. So, and then they open sourced it. And so what we did is we took some of these models from Hugging Face. So let's compare the GPT, which is sort of the poorly trained model, the model that's trained on an insufficient data set. And let's compare it to a model which is trained on a high quality data set. And let's ask, how do they differ? And it turns out when you look layer by layer and you look at a picture of inside, you peek inside the model, what you find is the low quality model has this sort of the shape of the spectral density is a little goofy. It's kind of choppy here, not really a straight line. Then it kind of tails off, and then there's this large outlier out here. And when you look at GPT-2, it's much more of a straight line. It's sort of, obviously it's kind of bumpy, but if you look sort of at this fit, the fit on the left-hand side versus the fit on the right-hand side, you see the right-hand side is a straighter line. The alpha exponent is smaller. And this element here, the spectral norm is sort of this large outlier is gone. So what we found in general is that models that are better trained, the layers are more heavily tailed and they have a better shape. That's what we've observed experimentally. So we decided to take that idea and test it at scale. And so we've looked at, for example, here's every single layer in the poorly trained GP2 model versus the same model but trained on better data. And what do you find are two things. If we look at a histogram of the alphas, this is our quality metric. The quality metric gets smaller and more highly peaked. It's about 3.5 versus 4, and there are less outliers. There are less bad fits. So what we find is that when you have a model which performs better, its layers are more heavy-tailed and the fits are better. So this is the basic idea. And this is actually published in our Nature paper. This is the basic idea of the tool. So the tool allows you to look at the quality of your models and to ask, given two models, is one of higher quality than the other? And again, I'm not looking at the test data or the training data. I don't have the training data for GPT-2. I don't have it. Moreover, I don't even know how I would evaluate it because it's generating text. So you'd have to get a human, you'd have to read the test, you'd have to evaluate the quality, or you'd have to evaluate it on some proxy that an academic has created, like me. So this is just a very, very simple idea that allows you to analyze the quality, to compare the quality of two models that are the same, but have different amounts of data or different hyperparameters, and you can tell which one will perform better. We've looked at this point, hundreds of models and thousands of matrices, and this is a paper from a few years ago, so we've extended this. All models look like this. They all have alphas that are near 2. Some of them drop a little below 2. Most of them tail off at about 6. There are a few that have bad fits, but 80 to 90% of our layers have this behavior which lives inside what we call this fat-tailed, heavy-tailed universality. And so we believe that this is a sort of universal feature of well-trained models. And you can use these experimental observations to tell you if your model is performing well or not. From this, we developed a theory, which is called the implicit theory of self-regularization. We published a paper on it. And basically what we do is we say, how does a neural network evolve? How does it learn? What is it doing when it's learning? What it's doing is you start off with a matrix, a layer that is random. You haven't learned any information from the model, from the data. The models learn no information from the data. As training occurs, or in this case, as you increase the regularization, in this case, we decrease the batch size. As you do this, information starts to concentrate in the large eigenvalues of the matrix. And these eigenvalues start to pull out. And we have plots, and the tool will automates all this. You put in a layer, it will automatically fit this to random matrix theory. It will identify these spikes. It will count them for you. It will tell you how many there are. And it will monitor as your model goes through this process of learning. And these spikes represent the bulk of the information content that the model's learning. And as the model gets better and better and better, it goes from being this random semicircle to being something that's heavy-tailed. It doesn't look like a circle at all. It looks like a power law. And it's this onset of power law behavior, which we believe characterizes the learning over in these very, very well-trained models. Now we can sort of nerd out on this, and I can show you there's lots of, random matrix theory tells you a lot about what the shape of these spectral densities, what these curves should look like when things are random. And so in other words, the less random your layer is, the more it's learned. And so here's an example, like if you zoom in at AlexNet, which is an older visual computer vision model, and you zoom in on one of the layers, FCC1 or FC2, the fully connected layer, you see this is what it would look like if it was random. This red curve would be a random matrix, and the bluish purple is reality. And when you zoom in, you find out, here's the same, here's another layer, FC2. You zoom in, you find out, oh, you thought that the red layer was, the red line was a good fit, but actually it doesn't really fill in this part of the bulk, and it sort of tails off. So, you know, the more you've learned, the farther away you are from random, the more heavy-tailed you are, the more you can tell that the system has learned some information from the data. And this occurs layer by layer. And this will allow you to create a diagnostic. You can use this as a diagnostic tool to figure out if your models are training properly or if certain layers are not trained properly. And again, the idea is that, and this is an idea that comes from quantitative finance, as you get very, very well-trained layers, these models become heavy-tailed. And this, by the way, this is right out of looking at market data. So a lot of the theory we're using comes from people who study the stock market, and they're trying to create portfolios. They're trying to understand correlations in the market, maybe when the market's going to crash. And they know that this behavior occurs. There's another question. I'm going to try to read it. How does the model compare to cross entropy of networks? We can look at, here's a question. So someone wants to ask, how does this compare to looking at the cross entropy? So you can, I can actually give you an example of this. I'll go forward a little. Let me give you an example of what you can do when you look at entropy metrics. So here's an example of some work that was done by a fellow on our, so we have an open source Slack channel. And here's a fellow, James Hershen, who's done some work with us trying to understand, can we characterize the randomness in each layer, and can we look for problems? So here's an example of looking at various kinds of metrics. Entropy, looking at the total entropy. You could look at the cross entropy between matrices, between models. You can look at the alpha metric. You can look at the scale, or you can look at how different is the model from random. And you can, so to answer your question, using the tool, what you want to do, we have these various metrics. We can measure, like, you know, cross entropy between layers. What you're trying to do is ask, if you begin fine tuning a model, does one of the layers collapse to random? And so by using the tool, you can see, here's an example that he found where he was fine tuning Albert, I think. I don't remember the exact model. We did so many of them, but he found, hey, look, layer 2 collapsed. Layer 2 became random. So during the fine tuning process, the layer collapsed. And we think that this may be an indication of catastrophic forgetting. So by using the various metrics in the tool, you can detect these problems. And what I want to point out here is that if you look at just the entropy of the layer, there doesn't appear to be any difference between the entropy. Like, the entropies look the same. The spectral norms look the same. But when you look at the random distance metric, you see something very different. So to generally answer the question, how does this compare to cross entropy? My answer is, you've got to look at a lot of different metrics. Different metrics behave differently in different ways. And what you're trying to do is, if you're looking for a problem, is you're trying to ask, does something collapse? Does something break when you're fine tuning your models? And that's what the tool does. And we don't know why is the spectral norm the same, but the random distance, you know, different metrics are more sensitive in different situations. So I'll give you some examples of things you can do with the tool, which are maybe a little surprising. Here's sort of our theory, where we talk about the theoretical aspects. You can read, it's our paper. We talk about, we call it the 5+1 phases of training. But the main point is you're trying to get down to this phase of training where you're heavy-tailed. And if you're up here and you're random-like, something's wrong. And the tool lets you compare random versus non-random layers automatically. And it, you know, the tool has things like, it tries to auto-calibrate the layer, right? Because when you run these models, the layers shift in norm. That's why people try to control the batch norm. So the tool allows you to calibrate the layer automatically so that you can do these comparisons. That's sort of the magic inside the tool, which would be very painful if you tried to do it on your own. There's another question. Oh, thank you. Okay. So those are the two. Okay. So I won't go through. We have a lot of theory where we talk about sort of, we match what we're doing to various universality classes and heavy-tailed random matrix theory. More interesting is I'll show you this as a result from trying to predict the test accuracy. One of the things we found that we can do is if you take a model and you fix the number of the depth and you vary the hyperparameters, we can actually tell you on average which model will perform better without looking at the test data, simply by looking at the average, the weighted average, this alpha, this one. The average alpha will actually tell you which models perform better when you vary the hyperparameters without looking at the test data. So here's an example. There was a contest by NIPS, and they gave the NIPS NeurIPS contest. They wanted to have a contest on predicting generalization. It's kind of, we actually submitted a paper on predicting generalization. They rejected the paper because it was too empirical, and then they had their own contest, based on our suggestion. That's okay. So we took the contest data and we asked, can we predict the generalization? Give just by at each depth. So we fixed the model. So they have these different models that they trained with different numbers of layers. And we found that some models had very high test accuracy, like 95%, 90, 95%. Other models had pretty poor test accuracy. And what we found is that when we apply our theory, the more accurate the model is, the better the theory applies, because you're doing a power law fit. So when the fits are better, when the accuracy is higher. And moreover, the actual exponent itself of the power law fit is remarkably correlated with the test accuracy. And when you have low accuracy models, it's also correlated, but obviously the correlation is much weaker because the fits aren't that good. And as you get better and better, the theory becomes more and more accurate. So we found that if you have a model and you're just varying the hyperparameters, you can look at the alpha metric and it will tell you which direction you should be going. In other words, this model is this version of the hyperparameters gives you a model which is less accurate than this one. And if you want to change the actual number of layers, we have a way of doing that called alpha hat, which is a weighted average of the alphas. And this also correlates well, and it gives you a nice behavior if you want to ask, are the models with less layers more higher or lower accuracy than the models with more layers? And so this works for models both in changing the hyperparameters and in changing the depth. And again, we've looked at this across, like, say, VGG models, looking at VGG 11 all the way to VGG 19, and our alpha hat metric correlates remarkably well with the test accuracy of these models. We've looked at other metrics like our weighted alpha, our Shat norm are similar. We've looked at ResNet, and when you have all the ResNet models, you even get a pretty good correlation. There's a little bit of a drift, but it still works pretty well, remarkably. Again, this is published in Nature. We've looked at hundreds of models, and this is systematically pretty good. And we've shown that it works better than other metrics that people have suggested. So sort of the results from the Nature paper. Other things you can do with the tool, you can study the correlation flow. So for example, you can look at your architecture and ask, how does information transfer through the model? So here we have an example of 3 different models, VGG, ResNet, and DenseNet. These are computer vision models. And we asked, let's look at layer by layer our alpha metric and ask, how does alpha change when you change your architecture? So in these models, VGG is sort of an old-fashioned computer vision architecture. It was, a convolutional layer, max pooling, convolutional max pooling, convolutional max pooling, then a couple fully connected layers. And what you see is, as you move through the convolutional layers, alpha actually, and as you look at the beginning near the data, alpha is quite small. We actually think it may be a little overtrained. The first few layers may be a little overtrained. Then alpha starts to systematically increase. You get harder and harder for information to flow through the network. And then boom, these fully connected layers at the end have small alphas. They recapture the information. So we see why you have to have convolutional layers, which you push the information through, and then bam, at the end, you put these extra fully connected layers on to reconcentrate the correlations. In ResNet, the idea was that you would have sort of connections between layers to help the information flow. And, people have understood that you need to do this. And it turns out that our theory shows, in the ResNet models, it's better to look at the longer ones. You can see it better. The information doesn't get bottlenecked up like in VGG. It flows through. Obviously, there are some outliers, but it flows through the model, and then only toward the end doesn't. And these are basically just bad fits. So this, I wouldn't even care about this part. What matters here is that in ResNet, it's only when you get to the end that you start seeing the sort of the correlations drop down a little. The whole model, the residual connections allow better flow through the network. Well, then you might think, well, if I have residual connections, let's just put them everywhere. That's what DenseNet does. And when you put them in DenseNet, it just goes crazy. Like the alphas are all over the map. So what happens is that the tool will allow you to study various types of architecture patterns that you might want to use to train your own neural network. It lets you examine these patterns, and it will tell you which patterns have good correlation flow, like ResNet, which patterns are bottlenecked, like VGG, and which ones are just crazy and unusable, like DenseNet. And so it allows you, if you're designing your own neural network, it allows you to characterize the flow. And again, no, you're not looking at the data. You're just looking at the model. So somebody else can train the model. One person can train the model. Somebody else can analyze it. We have some examples of trying to use alpha as an early stopping criteria. Also, this is some interesting work that was done by someone at a hedge fund. I can't reproduce this work, but he was showing this to me. I thought it was so remarkable what he showed me that I put it in the plot. But again, this is unpublished and experimental. But in this case, there was a fellow at a hedge fund trying to train a transformer model to predict the markets, right? And when you're trying to predict the markets, well, you don't have access to the test data because that's the market data. So if you look at the test data, you'll overtrain. You always overtrain. So instead, he looked at our alpha metric, and he studied the training and the validation loss of alpha. And he found that when alpha hit 2, the validation loss stopped going down and started going up. Boom, right here. This is where it happens. That's exactly where our theory says you cross from the fat-tailed universality class to the very heavy-tailed universality class. And we suspect that when alpha is less than 2, the model may be overfit. And that's exactly what he was seeing, is that when the validation loss starts to increase, that indicates that you're beginning to overfit, and this is where the early stopping would happen. And usually you just look at the validation loss for early stopping, and he found that alpha actually correlated with that. The reason we think this is happening is because there's some work in physics that shows that alpha is a measure of the local convexity of the layer. And so the average alpha is sort of an average global convexity metric. And what happens is, this is what we think is happening, is that and this is, again, this is from somebody else's work. The theory of why alpha would be a local convexity metric is from an old theoretical physics paper in the 90s. These plots come from people looking at ResNet versus, these are vision transformers. And what you find is when you look at ResNet, you find the alphas are 2 or 3 or less. And recent research shows that the global optimizational landscape is quite convex, maybe a little too convex. And when you look at transformers, we find that the alphas are between 3 and 4 are the best alphas. And recent research shows that in transformer models, the loss landscapes are not, they're still convex, but they're flatter. And so the flatness basically says, if this is my training data, my test data is out here, sort of, it says that you don't want to have the optimization landscape or the energy landscape changing too radically when you move from training to test. So this is saying that the model is concentrated on the training data and will have trouble predicting the test data. This one says that the test data and the training data look very similar. And we believe that our alpha metric, and this is theoretically why we did it, the alpha metric is a measure of overfitting. It's a gross measure of the convexity of the landscape, and gives you some idea whether your models are overfit or underfit. So, and basically we suspect that in a lot of the earlier layers in convolutional nets may be slightly overtrained. And this is actually predicted by our theory. We predicted this several years ago, and now we begin to see that some results coming out. So Again, the tool allows you to detect things. It allows you to detect problems layer by layer. Here's another example of, here's an example. We were talking to the group at Intel, and they have this technique called group regularization, which allows them to shrink a model, basically to compress it to get onto the hardware so you put it in the car. And we found that there was one specific case of called group regularization, which is one of their compression models, where the spectral norm, if you measure the spectral norm in the baseline was quite small, and when they fine-tuned it, it exploded. And generally, when the spectral norm behaves like that, we think it's anomalous. We don't know what happened, but something changed in the compression. If you look at the alphas, they don't really change. There's no real noticeable change, but something happened in the spectral norm. And so again, we pointed this out, that the tool is used to look layer by layer, because it's not clear to us, if the spectral norm blows up, is that good or bad? I mean, it might be good. It actually might have improved the model, but it definitely would change the performance of the model, because you've changed the scale of the layers. And we're concerned that, when you do something like compress a model to put it on hardware, or you want to do inference, we want to check layer by layer to see that the metrics haven't gone crazy. The final thing we can do is we had talked earlier about comparing models layer by layer and looking at how different they are from random. So we actually have the ability to look at, I think someone was asking about the cross entropy. We have a metric in the tool which compares the entropy between the original layer and its randomized form. So if you take the original weight matrix and you randomize it, and then you measure the Jensen divergence between these two distributions, you get something called, I won't go into the pack bound stuff. You have something called the Jensen-Shannon divergence, which measures basically like a cross entropy between these two layers. And you find that that is remarkably correlated with test accuracy as well. There was a question, can your metrics be used to guide backprop during training? Yes, why not? But typically, so the question becomes, can we use these metrics to guide backprop? Typically, backprop requires that you have something which is differentiable. Because you need, typically, like if you come up with a regularizer to guide backprop, you want it to be differentiable. In principle, you could compute the spectral density in some randomized, using some differentiable form of SVD, and you could develop a regularizer from that. We haven't done that, but in principle, you could. It is non-trivial to fit alpha, because alpha getting the alpha fits is actually kind of tricky, and we have to do a brute force search. So probably for a regularizer, you might try to do something like regularize the stable rank. I don't know how you would regularize something like this, because again, if you want it to be differentiable, here what we're doing is we're randomizing the matrix and then computing this difference. But I don't know, how would you you would have to have some sort of sampling technique in order to integrate the randomization into backprop. So the question is, whether we can integrate this during training. We haven't focused on trying to build a better regularizer or to enhance backprop. What we've focused on is building an alert system. So downstream in the production process, you can detect problems. I do a lot of consulting work with clients, and I can tell you the problems are never in training the models. That's never where the problems occur. The problems occur when you get a model in production and it breaks, and no one has any idea why it broke. And 6 weeks later, you find out the model has broken. Somebody changed. This actually happened in one of my major client, one of the largest companies in the world. Somebody changed the logging system. The logging system broke. They stopped logging like the purchases weren't being logged. The data wasn't getting to the model. This wasn't detected till a few weeks later. Now we have to go back and fix it. Of course, now you've lost all that user interaction. So it's critical in any production environment that you have monitoring tools that can monitor when something breaks, so you can intervene immediately. It really is a tremendous problem. And that's why we developed the tool. But nevertheless, these things, you could in principle use them in backprop. Here's an example we show you with using the random distance metric. The random distance metric in alpha is very, very well correlated. So if you take the layer alphas and the random distance, this Jensen-Shannon divergence, it turns out that you can use the random distance to track epoch by epoch how well your model is doing. So if you're training a model with backrub, this is a postdoc, Yao Cheng, who worked with myself and Michael Mahoney, and he trained machine transformers for machine translation from scratch to state of the art. And by tracking by doing a truncated power law fit, you can do truncated power law fits as well, and you can track this metric, or you can track the RAND distance metric, and either of them do very, very well at tracking the blue score epoch by epoch. And so we now know we can actually look epoch by epoch at a model and tell you how well the model is training without having to compute a blue score or any other kind of, our metrics are comparable to other metrics people have, but our metric is data independent. You don't need any data to do it. So you can imagine a production environment, you can deploy the model downstream, you just upload the models, you don't have to look at training data, you don't have to integrate your data pipelines into the model evaluation. And that's really the key, because in a production environment, data pipelines break. So if you're going to do any kind of evaluation, you have to have some sort of data independent, some data-free diagnostic, because the primary problem that happens in any production environment, 9 out of 10 times, your data pipelines are breaking. So we've tried to come up with a tool for our clients that would detect these problems in your models without having to actually integrate them into your data pipelines. So I'm going to kind of stop here. It's been 40, and I'll open the, I'll make one more comment actually before I go. There actually is some deep theoretical reasons why this works, and you can build a theory from physics to do it. But it turns out that we also know something about the behavior of actual spiking neurons. So if people study cultured neurons, you look at neurons in the lab and you culture them and you study their correlation behavior, in this case, the spiking behavior, and look at something called an avalanche, it turns out that there are these fits you can do which will fit the avalanche sizes to a power law. So avalanches are basically when you see clusters of spikes like this. Here's a cluster and here's a cluster. Here's a cluster. The size scale of these avalanches that occur in these spatial temporal avalanches exhibit power law behavior. And this is based on a theory actually developed in the 90s by a guy named Purbach called self-organized criticality. So a lot of people believe this is evidence of the onset of self-organized criticality. So the system is self-organizing to learn. And it turns out that this is related to the critical brain hypothesis, which suggests that living brains, living tissues behave, they actually exhibit power law behavior because they're operating on the edge between order and chaos. And in simple systems, you don't see the behavior. In a complex neural network, you see power law behavior. And in very, very complex neural networks, you see truncated power law behavior. And that's exactly what we see in our models. In the simplest old models, you don't see any power law behavior. Random systems, you don't see it. At a coarse grain level, when you look, you see power law behavior, and the power law exponents are correlated with the generalization capacity of the model. And this corresponds to, in the critical brain hypothesis, that the power law exponents are a type of measure of cognitive complexity. And in very complex systems, you have to fit them to truncated power laws, and the tool will do this. And you get very, very accurate results in very, very large high performance models. So we see the exact sort of behavior, and the idea of doing the power law fits actually came from these ideas in experimental neuroscience. So I'll just leave by saying this is an open source tool. You know, I do consulting work, but this is a tool we provide for. It's an open source tool. We don't charge for it. You know, it's a specialist tool, obviously, so we use it as part of our practice. There's a Slack channel to support the tool, GitHub page. You can download the tool if you find it's a work in progress. Basically, it's me working on this in my spare time, especially since the pandemic. So it's that, and we have a Slack channel if you want to use the tool. Join the Slack channel, ask me questions. I really haven't, since the pandemic, the business has kind of slowed down. So we haven't really spent a lot of time documenting and featuring it. We just go and give these talks. We have a Slack channel. Try the tool out, join the channel. We're looking for people to be early adopters and collaborators. So I will stop there and open the floor to questions.
I think there was a question in the chat earlier.
Let me see.
Did you?
Yeah, it was the question about using it during back prop.
Yeah.
So I hope I answered that, but if you
Okay.
have additional questions, please ask.
Yeah, sorry, I missed the
That's no
answer.
worries.
Okay, can I ask you a question to use some kind of intuition? Are
Sure.
we trying to measure how well the information disseminated across neurons?
Yes, yes. What we're doing is we're looking at how we have a neural network. It has various neurons at each layer, and we look at how the neurons learn the information. Exactly.
Yeah.
And we use techniques from computational neuroscience to do it.
Yeah, I need some kind of intuition too, because I'm not so strong in statistics anymore. But
yeah, the talk is a little technical.
Yeah.
But that's exactly what's going on. You have the neural networks are a bunch of layers. Each layer contains neurons. And what we've done is we've gone in and used techniques from experimental neuroscience, which we know something about how neurons behave. And we've developed sort of a measure of neural complexity. And we measure the neural complexity layer by layer. And remarkably, the neural this crazy idea from neuroscience actually works in these artificial neural networks.
Then another controversial question, but then we don't need testing anymore.
Well, that's my goal. You know, if you ask, we talked to the head of AI at Intel, and he said, "Look, you know, I got to put this thing in a car, you know, we have. How do you test it? How do you test every single example? Right? How do you test it? I mean, you have to basically build a simulator.
Yeah.
And so that's why people have these artificial realities. You know, you have this, you know, you basically, you put it into a game like Grand Theft Auto, and you ask whether it can play the game. Yeah. Why? Because that's the only way to test it. You could not possibly, or, you know, you run it in Tesla while the cars are running, and you have the thing running all the time. Yeah. Even though it's not driving, it's still collecting data, and you're testing it whether it actually made the correct decisions. Sure. And that's the problem. And so, yeah, exactly. And look, I can tell you in the environments I work in with clients, some of the clients I work with the work is very compartmentalized. You know, this group in India built a logging system. This group in Mexico is analyzing the data. This group in Europe is building the database. Like, and it's completely, the companies are completely compartmentalized. And somebody builds a model, and it goes down the pipeline, and somebody deploys it. A bug happens because somebody changed something over here, and it breaks the model. There's no way, and it'll take 3 months to figure out what happened. Meanwhile, you know, revenue is tanked. Yeah. You've killed, and I mean, I see this happen all the time. So like, you need to have these sort of model monitoring tools, and that's sort of the pitch. Is, you know, how do you test something? You know, it's so hard to test things. Because not that you don't need it, but it's really hard to test things, because how do you test in a live environment when there are 100 things changing? Yeah. And that's reality. That's how large organizations work. Now, somebody asked the question.
Yeah, James. Yeah.
Can WeightWatcher be used with custom models? Yes. Yeah. In fact, that's where using it, for example, to study fine tuning and transfer learning. And then that's where the random distance is really the key, because it gives you that sort of fine grained analysis. That's exactly what we want to do. We want to know, we've seen cases like where you fine tune out. We've seen cases where you're fine tuning something and only 1 or 2 layers will change. Or we've seen cases where you try to do like we have cases where you train something adversarially for adversarial robustness. And what happens in adversarial robustness, you have all these layers, and one of the layers just becomes random. Like somehow randomizing the layer in some weird way, or destroying its generalization capacity, somehow makes it adversarial robust. We don't know why, but we know we see it. So that's exactly what the tool is used for. And we're hoping people will use the tool and then come back to us, and we'll, you know, give you feedback on how to use it. And that's the idea.
Happy to test it. Anybody else? Yeah. Anybody else?
Useful for students. Yeah, no, no, there are a lot of things for students to do. It's a wide open field. You know, this is something that is there are a lot of things we don't understand, right? A lot of things, and very few people are looking at, a lot of people when they, how do people train models? They just sort of, you just blindly vary everything by brute force, and you see how accurate you get. And that's no way that you can build an engineering discipline that way. You have to have some reason why things work. And so there are a lot of questions for students to ask. Absolutely.
Yeah.
Okay. Anything else?
Any other questions? No. Wow.
Well, I'll leave it at that. I really appreciate you
That
letting
was
me
great.
come and
That
talk
was
about
great.
it.
That was
I try to give a tool. I try to make it less theory. Just say, here's the tool. Use it. Try it. Use it. If you're doing something, try it. Give it to students. Have them join the Slack channel. We'll interact. It really is. I want to get my hands on some of these really big models. Like the DALL-E or this new. You see this new thing that was developed by Google. It knows everything.
Yeah.
It can play video games. It can control robots. It can speak to you. It's just crazy, right?
Yeah.
And these are things that probably cost, I don't know, what did it cost them? $50 million to make. Who knows how much it cost them to build this thing? For them, it's peanuts. So I'm just amazed. Well, look, thanks again, guys. I really appreciate it. If you have questions, reach out to me. You can join the Slack channel. We really want to try to build a community around people who are interested in these things. And so the idea of the Slack channel is to have a community of people who are just interested in why these things work and are training models, and to try to get people to help each other to do it. And that's sort of the idea of having an open source tool.
Thanks so much, Charles.
Thank you. You guys have a great weekend.
Thanks.
All right.
Bye.
Goodbye.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.